This chapter is about the Big Bang, but I don't actually like how your textbook handles the first section. They give you a lot of information. So I'm not going to assign the first section of this chapter as reading at all, but I am going to talk through it, and you might need to know a couple of basic things from this first section. So what's pictured here is basically a timeline of the universe. The beginning, the Big Bang, the universe expands and cools, expands and cools. And a lot of really interesting stuff happened really early in the history of the universe, so we zoom in and go through some of the details there. Okay. But the simple story of the universe is going to be expands and cools. All right. So let's go through this step by step. So the Big Bang Theory is the idea that an event started the expansion of the universe and also created energy and space and time. So we would say that the Big Bang would be the beginning of the universe. Now, it is a scientific theory, meaning four things. It has quite a bit of evidence supporting it. We'll go through the bigger lines of evidence. It hasn't been proven wrong yet. It explains something natural in a natural way. And it can only be replaced by another idea that explains why this idea worked so well. Okay. So that's what we mean by Big Bang. It's the idea that the universe used to be much smaller at a single point, and then it started expanding and cooling. As we go through this, I'll tell you what evidence we have and what evidence we do not have. So let's say the Big Bang started at time zero. It created time, it created space, right at time of zero. For the very, very, very first fraction of a second, it would have been the hottest and the densest that the universe was. So it would be a very important fraction of a second to be able to understand, but we don't. We don't understand anything about it. We have no idea what it would have been like. We have laws of physics that tell us how particles behave in certain temperatures, and we don't even know if those particles could exist at these temperatures. So we really don't know. We have no way of testing it yet. We cannot reproduce the temperatures that existed back at this time. So I would say the very, very, very closest time that you can get to the Big Bang, and we know nothing about it. We have no evidence, we have no proof. Let's go a little bit further in time. Still a fraction of a second old. By that time, the universe should have expanded and cooled down to this temperature, 2 times 10 to the 15th degrees Fahrenheit. So that's still a huge number. And at that time, at those temperatures, the universe should have only been filled with particles and light. And particles would have been like electrons or quarks. And you may not have heard of quarks, but quarks make up protons. Quarks make up neutrons. So you are actually made up of quarks. Right. At those temperatures, the proton falls apart into its separate quarks. A neutron just falls apart. Okay. And we haven't observed this directly, so we don't have any direct evidence or direct proof. But if the universe ever was at this temperature, we think we understand what the particles would have looked like and how they would have behaved at that temperature, because we can recreate those temperatures indirectly inside of particle accelerators. We can get a proton moving up close to the speed of light, and we can hit it into another proton moving close to the speed of light and smash them together, which recreates those temperatures. We have to recreate those speeds. So we don't know that it ever happened, but if it did, we think we know what it would be like. From that time out to about 5 minutes, the universe just continues to expand and cool. Oh, look, it's down to 1.8 billion degrees Fahrenheit. Okay. It's cooling, but it's 1.8 billion degrees Fahrenheit. During this time frame, the proton can finally stay together, as well as a neutron. Not only can the protons stay together, and the neutrons can stay together, but they can actually bind together into a helium. So I like to think of this era of the universe as a gigantic fusion reactor. Right? So if we understand the temperatures that were involved, and the rate of the cooling, and if we understand the densities and the time frames, maybe we can predict what else might have been created during this time of fusion. So let's make a model. Let's look here at the top. This is time after the Big Bang. 10 seconds, 100 seconds, 1,000 seconds, right? And this vertical part shows how much of each element you would expect. During that era of fusion, you're making helium, so helium comes up. The amount of deuterium comes up. 2 hydrogens stuck together is called deuterium. An amount of helium-3, the amount of tritium, and you also have tiny amounts of beryllium and lithium being formed. So this graph is a model. We made this, we put math into it, and we're predicting the abundance of certain elements after this era of fusion. So let's go out and look at the universe and see if we're right. And our results are actually really good. The amount of helium and the amount of hydrogen matches what we would expect. The amounts of some of these other elements and isotopes also match our predictions. So I would call this our first evidence that the Big Bang actually happened. Our predicted model matches what we see out in the universe. After about 5 minutes, the fusion is done. The temperatures and the densities are not sufficient anymore for fusion, and these amounts are locked in. So let's go further in time after 5 minutes. So for the next 380,000 years, the universe is going to just expand and cool. Nothing much interesting happens, right? You've got helium, you've got hydrogen, you have electrons, and you have lots and lots of energy, or light. So that's all these squiggly lines, the light. So right now, the universe is a plasma, and it's going to be opaque, and you can't see through it, which basically means that these squiggles are trapped. The squiggles are going to hit a particle, get redirected, hit another particle, get redirected. So this era of the universe reminds me of the sun's radiative layer. And at 380,000 years, something really exciting is going to happen. The universe is going to expand and cool to just the right value where it no longer becomes a plasma. So I'm going to press play. The temperature is going to drop, and watch what changes. The light is trapped, bouncing between all of those electrons, and right there, it's cold enough for the electrons to recombine to the hydrogen and the helium atoms, and now the light is not trapped anymore. That is a big deal. Okay. So this is kind of like the sun. It's the boundary between the interior of the sun and the atmosphere of the sun. Okay. The interior of the sun is where the light is trapped, and it's bouncing around between all of these atoms. But once you reach a certain density of the sun, a certain temperature in the sun, that light is free and it just travels out through space, and eventually it just runs into Earth, and we get it. And we can see that light, and we can get a picture of the surface of the sun. So we're going to do the same thing here. So early in the universe, it was dense and opaque, and we couldn't see through it. It would have been bright, and then now all of a sudden that brightness is free to just travel through the universe. And if some of it comes towards Earth, and if we can take a picture of it, we will have a picture of what the universe looked like back then. So we're going to call this light the cosmic microwave background light. Right? It's the light that was trapped in the early universe by that random walk. And then once that change happened, once it got down to 5,000 degrees Fahrenheit or 3,000 degrees Kelvin, that light was free to travel through space basically until it interacts with something else, be it a nebula or a telescope designed by humans. Hot, dense material gives off a thermal radiation spectra. Right? So remember back to chapter 5. A cooler object might only give off infrared light. A hotter object like our sun would give off this spectra, and a hotter object would look bluer to us because it gives off a bit more blue light than red light. Okay. At 3000 degrees Kelvin, we would be right here. Right. This was the spectra of the universe when that light was trapped. Right. So that light at that spectra became free and started traveling through the universe. Right. So where is it? We look outside at night and we don't see this glowing sky behind the stars. That's because the universe has been expanding and the light is traveling in the universe, so the light has gotten stretched as well. So all of the wavelengths have been stretched, and so over time, because of the universe's expansion, the spectra has done this. Shifted into the infrared, so we can't see with our eyes. And actually, I can't take this demonstration all the way down to the right temperature. It's shifted even further than this, all the way into the microwave. So let's call it the CMB from now on. Stands for Cosmic Microwave Background, right? Right. Remember Edwin Hubble, around the 1920s, discovered that all of the distant galaxies were moving away from us. That got worked into the idea of the Big Bang. It's the idea that everything was closer together in the past. And so scientists kept working on this idea, trying to imagine what that would mean. And they predicted the CMB light. If the universe had ever been dense enough and hot enough to be opaque, there should be this background glow to the universe. They figured out what temperature it should be at. And if they know the temperature, they know the spectra that it should be at. And then they also worked out how much that spectra should have been red shifted over time, right? And so that's this line here. And the beautiful thing that makes me trust this with my life is that that spectra was predicted before it was observed. Right? That's different than the hydrogen to helium ratio. We knew the ratio of hydrogen to helium in the universe before we really knew about the Big Bang, and we're trying to work out the details of the fusion rates. I'm a little skeptical if your model matches the observed values, if you already knew what the observed values were, because you could subconsciously or consciously walk yourself to the right answer. You already know what the right answer is. But this was completely predicted with that spectrum before it was ever observed. Right? It wasn't observed until the mid-60s. And in the mid-60s, they finally confirmed the spectra. Right? And each data point that they took landed perfectly on that prediction. You can see these little bars coming up out of the data and down out of the data points. Those are error bars, just kind of indicating how reliable your equipment was. But they blew them up 400 times just so you could see them. So these error bars are all 400 times too big just so you can see them. The prediction and the data match amazingly well. Okay. So another fun part of the CMB story is that it was detected by accident. So in the mid-60s, Penzias and Wilson were working on their microwave antenna, which is basically a radio telescope. And they were going to use this to communicate with satellites out in orbit. But they always had this static in their antenna, and they couldn't get rid of it. They were trying to calibrate for it, trying to understand where it came from. They thought it might have been from human communications. They thought it might have been from astronomical sources, but they really just couldn't figure out where this static was coming from. They even ended up trying to clean all the pigeon poop out of their antenna, hoping that would make the static go away. And at some point, they were complaining about their problem to somebody else, and that other person happened to be working on the Big Bang Theory and made them stop and say, no, what are you detecting in your antenna? What wavelength is it at? How strong is the signal? I think you're going to be famous. You just found evidence of the Big Bang. You found the CMB radiation that's been predicted for years. So first thing you do is you just try to take a picture of this light, measure its strength in all directions. So here is an all-sky map from Earth's point of view, and it's filled with microwave light. Right? But we wanted to study it more in detail, so let's get even more accurate. Right? You get even more accurate, and you just look for the tiny fluctuations on that. Right? There's some regions that are a little bit higher energy. That's because Earth is traveling through space, and so we're blue shifting the direction where we're heading. And we are traveling through space going away from part of the universe. And so there's a red shift that we see. So we actually know our speed relative to the universe. Right? So now we found that effect. Let's take it out and look even finer at the details. So look at it even closer. Right? This is actually the Milky Way galaxy interfering with our picture of the universe, so ignore that for now. And there's the distant, distant, distant universe. The most recent and most high resolution picture we have of the CMB light is here. So this is a full sky map, and the galaxy was still impeding with our vision here, so some of this has been reconstructed a little bit. Right? But this is accurate above the disk and below the disk. That is how the universe looked when it was 380,000 years old. That light has been traveling for almost 14 billion years before it got to us. So this light is really old, and it came from matter that is really, really, really far away from us. That matter has since collapsed and formed into galaxies and stars, but we don't get to see that. That light hasn't had time to reach us yet. So the CMB light is amazing, and the more you study it, the more stuff you can learn about the universe. So if the universe had even more matter, the CMB light would look a little bit different. If the universe had a little bit less energy, that CMB light would look different. So because we see this pattern, it tells us how much matter is in our universe. It tells us how much energy is in our universe. It tells us the geometry of our universe. It's really amazing. So how should you picture the CMB light? You're at the present, and the further away you look from Earth, the more distant into the past you see. So you see galaxies when they were younger. Galaxies are forming about here, but they're so faint we can't see them. The CMB would have been released here, and that's going to be the limit of what we can see. So imagine if you could look behind all the galaxies, behind all the stars, we are surrounded by this light coming at us from every direction. Right? Behind that CMB light, there is more to see, but we can't see because it was opaque. Right? There is a possibility that we will someday be able to see beyond the CMB, but it's not going to be able to be with light. It might be with neutrinos. It might be with gravitational waves. So I'm excited about those possibilities. Right? One thing to think about here, the universe used to be smaller in the past. But in this picture, in this interpretation, the universe looks bigger in the past. Right? Because it had to be a bigger section of a circle there because it's further away from us. Right? That's why the CMB light is so redshifted, so stretched out. Because it's coming from, the universe used to be really, really small at that time. And then that small little piece had to be stretched to fill our entire sky. So it's really low energy light now. It's been stretched. All right. So let's go back to that overall map that describes how the universe has changed with time. Right, we had the Big Bang, which we have no pictures of and no direct evidence of. Right. We have evidence from about 5 minutes old because of the ratios of hydrogen to helium. We have amazing evidence from the CMB light when the universe changed from being opaque to transparent. And what's happened since then? The story has basically been expand and cool. Right? And as the hydrogen and helium cooled, that allowed gravity to clump it up. So once it got cold enough, gravity started to clump it up and form the small early galaxies. And then the galaxies began to merge. So you have bigger galaxies and clusters of galaxies. And at the present time, gravity is currently trying to pull clusters together to make superclusters. So that CMB light is now stretched and represents a spectra of roughly 3 degrees Kelvin. And so that's the coldest anything can be in our universe right now. Because if anything was colder than that, 1 degree Kelvin, 2 degrees Kelvin, it would absorb some of this CMB light that is just traveling through the universe, and it would be heated up. So I told you that the Big Bang is a scientific theory, which means it has a lot of evidence supporting it, but as time goes on, we might find ways to improve it. So we have already improved the Big Bang. We have included inflation. The simple Big Bang was the idea that the universe started and then continued expanding at pretty much a constant rate. But that couldn't explain a couple of key ideas. It couldn't explain how the galaxies were able to form at the right time. Just the densities and the temperatures and the gravity wasn't working out right. It couldn't explain why the universe looked so smooth. Like if we look at the CMB light in the constellation of the Big Dipper, it looks identical to the CMB light in the direction of the constellation Orion. And it also explains why the geometry of the universe is flat. And what we mean by that is that if you were to add up all the angles in a triangle, it should add up to 180 degrees. But if all of space was curved, that wouldn't be true. The triangle would have more than 180 degrees or less than 180 degrees. Before Edwin Hubble, people believed in a steady state universe that was infinite. So basically that the universe was infinitely old, infinitely big, and it never really changed much. But if you think about what that would look like in the night sky, you end up with a problem. You should be able to see galaxies and stars at great distances. And so no matter which direction you look, you should be seeing a star or a galaxy. So the night sky should be as bright as the surface of the sun. But it's not. Our night sky is dark. So we call that Olber's paradox. So the fact that the night sky is dark proves that the universe is not infinitely old and big. And it turns out that we know it's not infinitely old because we can see the CMB light. But what about infinitely big? We don't know. It might be. We have no idea. We cannot see beyond the CMB. Even though the universe might be infinitely big, that light has not had enough time to actually get to us. So that solves Olber's paradox.